Hello, everybody. Welcome to the May 2022 final meeting of the NES-OSA 2021-2022 season. It is wonderful to see you all in person. I would note that this looks like one of the biggest attendances we've had, which is a really good endorsement of the fact that people in the optics community want to see each other, want to form a community, and we're all kind of sick of the Zoom thing and excited to get back out into the real world. A great time for COVID cases to be back on the rise, right? So to lead us off tonight, we'd like to have Steve Fantone from Opticos give a few minutes of telling us about why we're here and himself and everything about this wonderful place.
Thank you, Joshua. It is really great to have everyone back here. It's been 3 years since we were last held our main meeting here. 2 years ago, we had invited Donna Strickland to come, the 2018 Nobel Prize winner. She was unable to come. We were unable to be here, but she provided us with a great evening and a really personal interaction via Zoom. And that sort of set the tone for the next few years as far as how we were going to interact with each other. We're all here tonight. I want to thank a few people. First, Lisa, please raise your hand. Lisa does an incredible job of making the rest of the staff of Opticos look good. And these events would not be anything like what they are without her work and dedication. So again, thank you. John, thank you for stepping up. Everybody at Opticos jumps in where need be. John is our supply chain manager, and he's right there clearing dishes and making this a great evening for everyone. These meetings, I think, are really important for our community. One of the things that delights me tonight is the number of new faces that I've seen. When I first came to this area, it was 1979. I didn't go to a local section meeting for 2 years because I was too intimidated by the people that might be there. It was inside a restricted facility. There was a real barrier to entry to come in and participate. And I want to make sure, one, everyone feels welcome here, and two, that when you go back to your communities, please encourage people, particularly people that are early in their careers, to come be part of this community, because ultimately, you know, I see people here tonight that I've only known through the Optical Society, and people like Alan DeQ, and you know, I first met him at one of these meetings, and they've become really lifelong comrades as we've fought the battle of optics over the years. So it's really nice to be here. Again, I want to thank the leadership of the New England section, and in particular Hillary. She is not here with us in physical presence. Anyone who has seen her knows that she's within a few days of delivering her first baby, and I just want all of us to congratulate her in advance for that day. So let's give her a round of applause. With that, I'll turn it back over to you, Joshua. Thank you. Oh, two other things I wanted to mention. Out in the lobby, there is a clock. And I just wanted to encourage you to stop by and see that clock. That was a clock that was created by Eugene Conradi in 1902. And for those of you that were optics people, lens design people, Conradi was Kingslake's father-in-law, his wife Hilda's father. He built that clock before he was into optics. And he solved the problem of how do you synchronize clocks in large factories in which there might be one main clock, and yet it wasn't really clear how you would get clocks on other floors to synchronize. I was up visiting Duncan Moore a few weeks ago. Duncan had been given that clock by Rudolph Kingslake. And he said, Steve, I don't know what to do with this. I don't think that the university, if I gave it to them, it would just disappear into their archives. Maybe you can do something with it. We are going to be doing a adaptive restoration to that clock so we can show how they synchronized clocks in 1902. Similarly, in the Baker conference room, which is behind that person who was drinking, is a little bit of a science fair kind of project. It is something that looks like it has a uniform white field, and behind that is a rotating polarizer. And it answers the question as to whether or not your eye can detect polarized light. That polarizer is rotating, which means this phenomenon called Hagin's band rotates in synchronization with that polarizer. It's a fun thing to see. It's a very subtle effect. Once you get trained doing that, you can actually see that in the blue of the sky on a beautifully clear spring day, fall day. It's amazing that you can see it. One of the reasons I wanted to mention that is that there's a book there, page 96. It describes what you'll see, but that was done by Stanley Ballard. Stanley Ballard was one of the original founders of this local section. We're coming up on the 75th anniversary in 2024. Fine point, May 5th, 1949 was the founding date when they were accepted as a section of the Optical Society of America. They had 3 meetings prior to that as the New England Optical Society. So I think that actually next year may be the 75th anniversary of their founding. So it's got a great legacy, great history, and thank you all for coming here today. We're very happy to be able to host this event.
Thank you very much again, Steve. It's wonderful to be here at Opticos. And we're really excited for everything that's going to be happening in the next few years of the society. Hopefully we'll have at least 75 more. So before we get into the amazing speaker for tonight, we do have a little bit of council business and a few slides where we need to thank the people who've sponsored our organization through the year. So the first thing I want to go over is meeting attendance, even though it was via Zoom, has been consistently relatively high over the past year. The appetite for continuing to attend through the pandemic when we couldn't be together has still been with us. There's been a lot that the council has done in the last year. One of the biggest items that, to mention is that we've had the largest changeover of council officers in a decade. We've had a lot of people really be instrumental to the growth and health of the organization. And one person that we really want to highlight is Groot Gregory. So I want to give him a big round of applause. I think it's fair to say that no one has been more instrumental to the continued success of this organization than him over the past 2 decades. We've also relaunched our corporate sponsorship program, and you'll be hearing from some of the corporate sponsors tonight. This is an opportunity for companies to participate in the organization in a financially meaningful way to us that may not be so financially meaningful to a larger company. That really helps us put on the programming that you see and really helps us bring in the sponsors and the put on the programs that we've been having this past year and for future years to come. We've created a social media chair position, recognizing that we are in the 21st century and it's time to embrace LinkedIn and recruiting via Facebook. Huge thanks to Erin Sumpleth, who's unfortunately manning the front desk. She's not with us, but she will be around this evening. We've also embraced the name change, or maybe we haven't. You'll see that the election results are a little indecisive. You can see that we did not get around to changing this slide to reflect the election results, and you'll see why. And then the upcoming event that we're very excited for is we're revamping our digital presence and moving over to a new website that has an integrated way of managing our membership. If I could ask everyone on Zoom, please mute. I think I hear a few.
Okay, so this isn't the speaker yet.
No.
No, it isn't. And then I think that was our last slide item on that. I'm Josh Brown. I'm our treasurer this year. Our financial situation as an organization continues to be good. We have, because we've been all digital, we have not put on as much programming as we have in past years. And so our total expenditures have been low. The dominant part of our expenses have been sponsorship of science fairs this year. In the upcoming year, we're excited to be putting on more additional programming. And so our expectation is that your dues will be put to good use. Thank you for everyone who's a dues paying member. For everyone who's not, we know who you are. But we really do sincerely thank you for your financial support of our organization, and we're excited for where we're going in the 2022-2023 year. On that note, we have in fact had council this year, and we are mostly staying on, but we have a good mix of new councilors. So I'd like to announce that all of the folks standing for election on the new council slate have been elected, unsurprisingly. The one contentious question was, should the New England section of the Optical Society of America keep its current name or change its name to mirror the Optica branding of our national parent organization? And we are a very opinionated and polarized group, and we have no idea what to do with this result. Because getting the 9 for the no preference apathy position, that was really the cherry on top. So we're going to kick it over to the council, the new council that's been elected for the 22-2023 year, to decide where we go vis-a-vis changing our branding going forward. Lastly, we want to give a few special shout outs and special thanks. The 2020-2021 council with President Peter Clark really helped set the pace and set the tone for how we would get through the COVID pandemic, and really set the tone for our transition over to a lot of new membership and new younger blood to come on and start making changes, keeping things the same, making mistakes and learning from the folks who came before us. So we really want to thank them for setting us up for success, failure, whatever it might be. We, of course, need to thank Optica, our parent organization, for continued financial and administrative support. Obviously, we're part of a greater and grander organization, and we're really thankful for everything that they do for encouraging optical science in this country and in the world. Of course, we need to thank Opticos for providing the amazing facilities they have. This meeting wouldn't be possible without them. Since we lost our ability to meet at Lincoln Laboratory, we've been somewhat adrift, looking for a home. Having this one meeting this year has been a phenomenal opportunity. We're really excited that we didn't have to go a full year without a meeting in person. Thank you, of course, again to Steve, Lisa, and Justin for putting this on. And a big shout out to David Lees. All of the speakers we've had this year have been incredibly interesting and really engaging. And I don't know how he finds these people, but wow, David is one of the most incredible folks for at encouraging and embracing speakers to come and speak to our organization. So a big thank you to David Lees for that. And then, of course, it wouldn't be possible to do all of this without our corporate and professional sponsors who fiscally keep our organization in a good place. So with that, did you want to do the corporate sponsors or? Okay. So we'd like to give an opportunity for just a couple minutes each to have the corporate sponsors who are in attendance tonight come up and give a quick blurb about their company. So I'm not sure who is and isn't in the room tonight, but if you know that you're going to be talking, come on up and we'll hand the mic over to you. Someone from Rudzinski Associates here tonight? Okay, I'll do the blurb for them. Rudzinski Associates offers professional organizations and professionals at all levels an unparalleled track record of success in talent acquisition and in career advancement and developments to advance the objectives of the organizations and individuals alike. Rudzinski Associates adds value as subject matter experts, SMEs, and career and talent acquisition related to aspects of optics, lasers, photonics, and engineering, including engineering, operations, manufacturing, R&D, and sales and marketing. So thank you very much to Rudzinski Associates for their continued sponsorship. Lambda Research Corporation. Do we have Ed in the room tonight? Let's see. Okay. Everyone knows Lambda. Lambda makes Oslo. What would we do without Oslo? Lambda Research Corporation provides world-class optical modeling software for ray tracing and illumination from their corporate headquarters in Littleton, Massachusetts. Their products include TracePro for analysis and simulation of illumination in optical systems, Oslo for optical system layout and optimization, and RayViz for visualizing ray paths in SolidWorks. So thank you very much again to Lambda Research. Optics for Hire is not here tonight, but they did give me a blurb to read. Hello to NES-OSA and friends. I'm sorry I cannot join you this evening. I'm coaching my 9-year-old daughter and her soccer teammates tonight. I imagine your meeting will have much better listeners, but fewer piggyback rides. Since 2002, Optics for Hire has brought the expertise of a talented group of Ukrainian and Belarusian physicists, optical, mechanical, and optoelectronic engineers to companies large and small in the US, Europe, and Asia. Since that time, our employees have worked on a wide range of programs from the first LiDAR lenses for Velodyne to optics integrated into Barbie dolls, objective lenses for national labs, the diffractive optical element used in Xbox Kinect, to light pipes on Ring doorbells, and dozens of medical devices. It's been our great pleasure to be part of such a vibrant industry with so many unique applications. While our team has grown, many of our employees have been with us since the beginning. The one important exception I want to mention is the business manager of our Lviv office until 2010, Denis Shimon, who became Prime Minister of Ukraine in March of 2020. As you can imagine, the last few months have been a challenging one for our company, but our engineers remain doing the work they love and are thankful for the support of the American people who have provided in their ongoing fight, that the American people have provided in their ongoing fight to protect their country. John Ellis. So we thank Optics for Hire for their continued sponsorship. I know that we do have folks from LabSphere in the room. So.
Hi everyone, my name is Lauren Loudon and I'm the OEM Business Development Manager for LabSphere. So LabSphere is located just north in North Sutton, New Hampshire, right in the shadow of Sunapee Mountain, if you're familiar with Sunapee at all. And LabSphere is a manufacturer of optical equipment. Our key technologies really are near Lambertian diffuse materials. We develop a lot of proprietary materials and integrating spheres. And so from those two base materials, we develop all sorts of light metrology equipment. And so kind of our 3 pillars are measure any light source, create any spectrum, or reflect any wavelength. And then from that, the imagination is kind of whatever you want, right? So that's all we have today. Thank you so much for having us.
All right. Of course, it goes without saying that we're very thankful to Opticos Corporation. Would anyone from Opticos like to give another quick blurb about Opticos?
Since you've heard from Steve, I wish I could show everyone. I'm Haskell, Ken. I wish I could show everyone the other 45,000 square feet that you can't see, focused on optical product development and manufacturing. You probably have heard about our metrology products for testing lenses and cameras, but we also do a lot of great projects on behind you, and behind that closed door is surgical stereo microscopes and aerial imagers and automotive systems and all kinds of fun stuff. So happy to have you all here. Thanks.
We also have professional sponsors, Fundamental Optical Solutions. I don't think Gulshan was able to make it tonight. Okay. Fundamental Optical Solutions, expertise in advanced scientific optical technology and engineering, provides first-class engineering services and fundamental solutions in new product introductions. Product development across all industries, whether consumer or commercial products to startups, mid or large companies, academia, and government. So we thank them as well. I don't think Linda Usher is in the room tonight. Linda Usher is an optics search specialist focusing on the recruitment and talent acquisition of optical scientists and engineers from engineering levels to executive and corporate leadership. Her years of experience and knowledge have led to hundreds of successful high-quality placements globally. So we thank her. And then finally, General Fluidics Corporation. Are they in the room tonight? Okay. General Fluidics is an in vitro diagnostics company that has developed a novel end-to-end fully integrated molecular IVD platform for performing a growing array of blood and urine tests. The Access platform uses a patented hybrid hardware architecture, fluidics, and optoelectronic technologies to go beyond the test results to deliver complete diagnostic information sets at the point of care. They're located on Trapella Road in Waltham and are always looking for qualified individuals to support their efforts. So we thank them as well. With that, we want to give one last round of applause to thank our professional and corporate sponsors for the year. And I'd like to introduce our speaker for the evening. When I was putting this blurb together, I noticed that it was a little long on the website to include everything in the introduction, and I started looking for chaff to cut, less impressive things that the speaker has done, and I realized I couldn't find any. So the things that were cut were prestigious fellowships and being the chair of major things. I'm impressed. Professor Daniel Eisenstein studies cosmology and extragalactic astronomy with a mix of theoretical and observational methods. His dominant focus over the last decade has been on development of the baryon acoustic oscillation method to measure the cosmic distance scale and study dark energy. Dr. Eisenstein received his Ph.D. from Harvard University in 1996 and then held postdoctoral positions at the Institute for Advanced Study and the University of Chicago. He was on the University of Arizona astronomy faculty for 9 years before moving to his current position as professor of astronomy at Harvard University in 2010. Starting in 2020, he serves as the chair of the Harvard University Department of Astronomy. And with that, I'd like to welcome our speaker, get the presentation up, and
Thank you very much.
turn it over to you. Thank you. Thank you very much.
I think that's it. All right. Well, look, it's a real pleasure to come out to meet so many of you today, and it's just this will be fun. I chose today to tell you about the James Webb Space Telescope because that's the new thing in astronomy that's in the news. Hopefully, you saw some of this already coming across the news feed on Christmas morning. My family was there watching on Christmas morning even before we got to open presents. And before we get into the James Webb Space Telescope side of things, I'm going to tell you about the kind of things that I work on with James Webb, which is looking at galaxies in the early universe. So I want to give you a sense of the science for the first half, and then we'll talk some about James Webb. Now, I did not, I really want to encourage questions, and there's many people here who know far more about optics than I do, but I'm happy to try to answer questions about the engineering side of James Webb as well. I don't know if we can. We'll see if the pictures show up here with the lights. We might want to consider dimming the lights.
He's working on it.
Okay, that's great. Let's see. So why is this not? Okay. All right. So we're going to start with the topic of galaxies. And of course, you're familiar with galaxies when you look up on the sky. They're these big, beautiful systems. These are pictures from the Hubble Space Telescope showing the grand spiral arms of nearby galaxies. Or these dust rings running through nearby elliptical galaxies. And they're really wonderful systems. These are the island universes of the cosmos. But they're also very complicated. They come in lots of different shapes and sizes and configurations. So you see here galaxies merging together or galaxies that can't quite figure out which direction they're going. And so we'd like to understand more about how galaxies actually form. So before we can get to galaxies, I need to tell you some about stars. Of course, galaxies, the dominant thing you see in galaxies is stars. And when we think about stars, of course, we are very familiar with the sun, But stars form over a wide range of masses, from things sort of 1/10 of the mass of the sun up to things more like 100 times the mass of the sun. And the mass of a star tells you a lot about its properties. And in particular, stars that are more massive have much higher central pressures and densities that's allowing them to burn their nuclear fuel more efficiently and generate the outward going radiation pressure that's actually going to keep the star from collapsing in. So if you have more mass, then you have more gravity, more compression, more nuclear fusion, and more outward going radiation to try to hold things up. So these massive stars are very luminous. The luminosity grows much faster than linear with mass. And so they're very luminous, but they don't live for very long. They'll live for a few million years and then explode as supernovae. And the other thing that's important about these massive stars is that they are very hot. Their surfaces are much hotter than the sun. So the sun is about 5,000 degrees, but these stars are more like 10,000 to 100,000 degrees on their surfaces. And that will matter in the next slide or two. Most stars are not massive. Most stars are low mass. And these live for billions of years. The sun's going to live for 10 billion years, but some stars will live for much longer than that. And eventually those stars, as they run out of fuel in the center, hydrogen primarily, will then expand out and shed their outer envelopes in these phases that we call red giant and red supergiant phases. And then eventually leave the core, not as a supernova, but leave the core as a white dwarf. So there's these big differences between the high mass stars and the low mass stars.
Sorry, before we go on.
Yes.
Presentation's not being shared via Zoom.
Okay.
I just got notification that I'm not actually sharing, so I apologize about that. So let's share. We should be good now.
Okay.
Thank you.
Okay, so I want to make a point about this, about the temperature of the outer part of the star, because that affects what you see. And as you likely know, hotter objects glow more brightly, but in particular, they glow with the peak of their emission further to shorter wavelengths, into the blue. And so the sun, of course, is a yellowish star dominantly. I mean, our eyes have sort of evolved to think that that's normal. But when you have a massive young star, then it is going to have its emission peak further into the blue, even into the ultraviolet, shorter than 0.3 microns. And the cooler stars, primarily either low mass stars or these red giants that are in their outer, where the outer envelope is swelled up and the whole star is cooled because of that large swelling, are peaking in the near infrared, more like 1.5 microns. So this question of like where the radiation is peaking is going to figure into some of the things I'm going to talk about. Oops, get back on this. Okay, so if you now think about what happens when you form a bunch of stars, like it just, at some time, some reference time, you form a whole bunch of stars. Well, you're going to form a range of masses, a few high mass stars, a whole bunch of low mass stars. And those high mass stars are going to win. They have more votes. They're more luminous. They're going to outshine everybody else. And they're very blue. So that makes the whole population look really luminous and really blue. But after a few million years, those stars start to die out. And as you move on in time to 10 million years, 100 million years, a billion years, the massive stars are all dying. And what you get left with is a population that's dominated more by the lower mass stars. So that the population is getting fainter and it's peaking its emission more to the red. And so you have this characteristic change in what the population of stars looks like, where when they're young, really luminous and really blue, and as time goes on, then they will become fading red. And a famous example of this, or an important example of this, is actually in the spiral arms themselves. So when you look at nearby galaxies, you see these beautiful spiral arms, and that is basically an optical illusion. You would like to think that the gas is forming into some whirlpool and that there's like really high densities here and low densities here. That's not what's happening. What's happening is that the spiral arms that you see are where the young stars have recently formed. And so those regions look really luminous and blue. And the other regions have almost as much mass, but they just don't have the young stars. So the spiral arms are primarily, I'll call it an illusion, but it's the pattern of star formation in the galaxies. It is not actually where the mass is really dominating. There are only like 10% variations in the density of the material. Okay, So when we go to study galaxies, we really want to study them across a wide range of redshifts. We really want to study them across a wide range of wavelengths, because looking at different wavelengths will probe different parts of these stellar populations and also other parts of the physics. So I've already sort of explained that when you look at the ultraviolet, you're primarily going to be looking at the younger, most massive stars. When you look into the near infrared, you're primarily looking at the cooler evolved stars. And beyond that, when you look further into the infrared, you start to not really be dominated by the stars themselves, but actually by little dust or smoke grains in the space between the stars that is absorbing starlight and re-emitting that at much cooler temperatures. So it's basically dust in the interstellar medium that is being warmed up by the starlight. As you go into as you go to other wavelengths, we do a lot of astronomy in the X-ray and the gamma rays. That's not looking really much at stars at all. This is actually mostly hot gas near black holes, near neutron stars, just gas at 100 million degrees for some reason or another. And then on the flip side, when we go into the millimeter and the radio, you're really, again, not so much looking at stellar processes. This is mostly relativistic electrons spiraling in magnetic fields, producing something called synchrotron emission, or it's gas in the interstellar medium, rotating at some low energy state. So it's important in astronomy that we use a really wide range of instrumentation to try to gather light from all across the electromagnetic spectrum, because every piece of it is telling you a different part of the physics of these galaxies or stars or planets, whatever you're studying. So as a result, astronomers have developed instrumentation and facilities that are specialized to different wavelengths of light, because you can well imagine you can't use the same facility for X-ray astronomy or for radio astronomy or for optical astronomy. So to give an example of this, this is the picture I showed before on the left of the Whirlpool galaxy. And this is a nice, obviously two galaxies coming together where we have a spiral galaxy here on the lower side, and on the top is a little elliptical galaxy falling in. And you can see the spiral arms, a little hard with the lights still up, but you can see the spiral arms. So that's what you get when you look at optical wavelengths. So in this picture, you're basically looking at, what your eye would see more or less. So blue light connected to the blue gun of the camera, red light connected to the red light of the camera. On the right, though, is a picture from an infrared space telescope, the Spitzer Space Telescope, where in this picture, the blue is at 3.4 microns, and the red part of the image is from 8 microns. And now you see a really different picture of these two galaxies, where the thing on the top looks blue and the thing on the bottom looks red. And that's because the bottom galaxy is a star-forming galaxy that's lots of dust and gas, and that stuff glows at 8 microns in the interstellar medium. The stuff on top is what's blue in that is actually the light that's coming from the old stars. So you can see on this picture very clearly that, although they look kind of similar in the optical, when you go into the infrared, things look really different. You're able to tell the difference between what's a star-forming galaxy, the stuff on the bottom, and what's a non-star-forming galaxy, the stuff on the top. Okay, so now having sort of introduced some things about stars, let's talk about galaxies. So galaxies are obviously collections of stars. And what's going on is that gravity is causing dark matter and gas to collect into relatively dense regions. And once you get into these regions, then the gas that falls in is actually falling at really high speeds, something like 200 kilometers per second, not per hour. And when that gas comes and hits other gas, then it will get shock heated up to temperatures of a few million degrees and eventually cool. And as it cools, it loses its pressure support and sinks towards the bottom of these dark matter regions. And eventually you get this relatively high density gas. It's not actually high density, it's one hydrogen atom per cubic centimeter, but you get these relatively high density regions that are sufficient to allow the gas to fragment and form and cool into stars. And then some of these stars are really massive and energetic, and they then heat the remaining gas and sort of drive the whole system into a self-regulated star forming process. So the galaxies are, these regions that are what you see in the stars are something on the order of, let's say, 50,000 light years across. But the dark matter, the whole region of the galaxy that actually came from is more like 1 million light years across. So the galaxies, the part you see is actually just the tip of the iceberg at the center, surrounded by large amounts of other material. So I will try to show this then in these movies, these are now simulations of that are run on a computer of hydrodynamic simulations that are trying to model the process of forming galaxies on large scales. And the first of these movies, so on the left, we have the formation of the dark matter trying to pool together. This is on very large scales now. So this scales like, this picture is probably 30 million light years across. So it's pretty big by these standards. And on the right is where the gas is forming. And you can see the gas starting to collect into these denser regions, getting heated up to higher temperatures and denser regions. And as you start to watch this, you'll start to see like flickers in those regions as the simulation has decided that enough massive stars have formed to try to produce a supernova. So this is all what I'm showing you here is all very averaged, like the scale of resolution in a simulation like this is of order a million solar masses. So we're not simulating individual stars here. This is all millions and billions and trillions of solar masses of material pooling together. And the hydrodynamics are not perfect. They are trying to simulate this motion on large scales and then make up what we call subgrid or approximate models on at the pixel level to try to simulate the star formation. So this is just to give you a sense of like what might be happening to sort of collect the material that would form a set of galaxies. And now this will be a simulation of a single galaxy. So this is now a region that's about 100,000 light years. And now you'll see the gas streaming in. So this is all the gas streaming in and whirling around and forming into a disk that will form stars. The picture on the bottom right there, that's in grayscale, is a sort of picture of the stars that have been formed in the simulation. You'll actually see that it will successfully form a little spiral galaxy as it simulates along. So what I'm trying to get across here is a galaxy formation, it has these trends. You're trying to collect gas according to gravity, transform that gas into stars, have the stars blow out and heat some of the gas. And that's the cartoon sort of basic picture. But the full complexity of it is really complicated because you really have, it's a fully three-dimensional problem. Lumps are falling in. It's not that there's some simple smooth thing coming out. This is now spinning this thing around to show you something about temperature, and then it'll keep forming. So you can see another knot about to fall in and so forth. So galaxies have relatively, there's a regularity, but there's also a lot of tumultuous events as they go along. I'll let this run just a little bit longer. So it was really only about 10 years ago, let's say, that these simulations got good enough to actually make things that kind of look like passable galaxies. Prior to that time, they were trying, but they would always form things that were way too small and just didn't have this sort of refined structure. And so it's been a delicate balance, of course, with better computing to try to do this. So I'm not involved with this work, but the illustrious TNG team does have a lot of people from the local area, both Harvard and MIT, contributing to it. Okay, all right, so that's the theory. And it's a very pretty theory, or it has a lot of aspects to it, but then you want to actually see if this theory is correct, and that's where things get hard. So you're always trying to figure out how do you actually observe things and then compare them to aspects of the theory. And there are some aspects of physical science where that's a relatively well-posed question. You can actually say, my theory is predicting this. I will go into the lab. I will build the experiment. I will really measure. That's going to, I can really do the test. Galaxy formation is unfortunately trickier to actually really do a controlled experiment in. Not just because I'm complaining that I can't go out and change the galaxies as an experimentalist would want to, but more delicately that you really are stuck with certain fundamental aspects of the problem. So a long time ago in a galaxy far, far away, well, light travels at a finite speed. So if a galaxy is far, far away, you must be observing it long ago. Like you don't get to choose that. And that's important because galaxies evolve over millions and billions of years. The whole story of galaxy formation takes a long time. Like the movies I showed you were 10 billion years of evolution, right? But you only get to see any one galaxy as a single snapshot. So we do not get to watch that movie ever in observational setting. You're always stuck with seeing one snapshot. And if you want to infer something about evolution, you either need to somehow get in there and tease apart aspects of that galaxy and figure out that like, oh, it looks like things were aging as they moved across here. Like it's all very circumstantial in that sense. Or you try to compare populations of galaxies. So you try to look at galaxies that are nearby, that are relatively old, get a sense of what those demographics look like, try to look at galaxies that might be 5 billion years away, 5 billion years older or younger, and see what those look like, go back to 10 billion years and try to put pieces together. So this is like basically taking snapshots of a baby nursery, a kindergarten class, a high school graduation, this group, and then some 50th college reunion, and then trying to figure out what must have been the patterns that caused that baby to turn into this other thing, person at the graduation to this person at the reunion. So that is a very indirect route to actually studying the problem. And that is, I think, one of the big challenges in understanding galaxy evolution. Okay, but to do this then, we need to compare these populations, and that means that we are always trying to observe galaxies at a range of ages, a range of look-back times, and that means we need to look at things where the light has taken billions of years to travel to us, which means that we have to look at galaxies that are really far away. And that drives us to need really big telescopes, because if you put something 10 billion light years away, surprise, surprise, it's really small and really faint. So you have to deal with that. Well, before we can even get to that, I need to tell you that if you just look at a picture, like maybe that picture, how do you decide which galaxies are the ones that are far away and which ones are the ones that are nearby? You might think, oh, I'll just look at the big ones, angularly big, must be really nearby. And you're sort of right, but there's a lot of things on this picture that are really pretty small. And galaxies in truth come in a range of sizes and luminosities, like in intrinsic sizes and luminosities vary a lot. And so it's actually not immediately possible to decide when you just look at a picture which ones of these galaxies are nearby and which ones are far away. And so that is the next thing that one has to try to get at. And it turns out there's a really nice way to do this, and that's called the cosmological redshift. So the universe is expanding, and you probably have heard of that. And what this means is that what that expansion means, because it's a confusing thing to say that space is expanding, it's like not super clear what that actually means. But I think the way to think about it, at least in this context, is that if I have some fixed object out there, a distant galaxy, the time that it's going to take for a light photon to come from that galaxy to us is getting progressively longer in time. If it takes 10 billion years for the first photon to arrive, it's going to take 10 billion years and 1 second for the next photon to arrive. It just, so the light travel times are increasing. That's, I think, what we really mean by the idea that the universe is expanding. It says it's taking light longer to get from one place to another. And what this means, what this implies, is that if you have some periodic signal, like the subsequent crest of a plane wave, then that means that the period of that signal is being stretched out. If something was clocking every 1 second, then because every subsequent pulse takes a little longer to get to you, that means that the frequency, the time between them will not be 1 second, will be 1.1 seconds. And so when you think about this as applied to an oscillating signal like light, this means that the period of the light has been increased, which means the wavelength of the light has been increased. So this is called the cosmological redshift. When light is emitted at a particular wavelength, we observe it at a longer wavelength. And in particular, if the universe has doubled in size since when the light was emitted to when we received it, then the wavelength of all the photons that are coming to us have doubled. So if light was emitted at 1 microns, it gets absorbed here at 2 microns. And this is so the amount of this shift depends upon the distance from us. And there's a famous thing called the Hubble law, which for nearby objects says that the amount of the shift, the velocity that you infer if you interpret it as a Doppler shift, is linearly proportional to the distance to the galaxy. So this is great. This says if you go out and measure the shift, then you can measure the distance, you can infer at least the relative distance to the object. If I measure twice as much shift, the object must be maybe twice as far away. If it's the Hubble law, maybe something else if you're not quite in the small distance limit. So you need to measure the shift. And if you just measured a single photon, that would be hopeless because they don't come with little labels that tell you what wavelength they were when they were emitted. But as you know, light gets preferentially absorbed and emitted by atoms at particular wavelengths. And so by looking at the whole spectrum of an object, you very often can easily infer how much things have been shifted. And I put an example here with galaxies from nearby galaxies. And you can see this characteristic pattern here, this little double notch. And you can see it shifting here from 4,500 angstroms to 5,000 angstroms to 6,000 angstroms, or 5,000 to 6,000, eventually out there at 6,000 angstroms. So these are not small shifts. So light that was emitted at 4,000 angstroms has gotten received at 6,000 angstroms. So if you're doing Doppler shifts, that's 50% of the speed of light. But it's very very straightforward to measure. If you can go and take a spectrum of the object, you can measure this shift very well. We do this routinely. And so this is great. So if you can go and measure these redshifts, you're in business for deciding which objects are far away. So what I'm telling you is the more shift you have, the longer the light has taken to get to you, the further away the object is, the earlier you're looking at it in that use population. So when we want to go and study the earliest generations of galaxies, and I'm focusing on that because that's one of the big drivers for the James Webb Space Telescope, we are trying to study these first generations of galaxies that start forming a few 100 million years after the Big Bang, when the universe was very, very young, very naive. So the universe is only like 5 to 20% of its present size. And that means that these galaxies are very far away, 13 billion years of light travel time. But it also means that the wavelengths have been stretched a lot. So I showed you that last picture of 50% stretch. No, we're going to be talking about things where the wavelengths have been stretched by a factor of 10 or more. So really, if you interpret it as Doppler shift, these are very close to the speed of light. That is not the way to think about it. You should think that the universe has expanded by a factor of 10 since the light was emitted. But this is very important from an observing point of view because it means that the light that was emitted in the ultraviolet or optical has been shifted way out into the infrared. So to study these galaxies, it's not enough to just build a large telescope. Sure, they're faint, they're small. You need a large telescope to go and see it. But it's not enough to build it large. You need to build a large infrared optimized telescope. And so that's what I wanted to, I wanted to get that point across. So James Webb Space Telescope is a large infrared optimized telescope. The reason it's optimized in the infrared is because you have to deal with this shift. Now, it's not just that the infrared is the best way to study, it's the only way to do this. And that's because neutral hydrogen, which, the universe has lots of hydrogen in it, so neutral hydrogen is around, requires a photon of 121 nanometers to be excited from the ground state to the first excited state. So if you have a photon of 121 nanometers, it comes along and hits that hydrogen atom, it bumps it up in energy level, a nanosecond later, it de-excites, re-emits the photon, but in a random direction. And so that means that there's enough neutral hydrogen in the universe that any photon that was emitted shortward of 121 nanometers, as it travels along through the universe, at some point will shift its wavelength to be exactly at 121 nanometers, meet a neutral hydrogen atom, out in interstellar space, and get scattered off in some other direction. So when we look at these galaxies, we do not see any photons that were emitted shortward of 121 nanometers. And now I tell you that light has been stretched by a factor of 10. So that means that you don't receive any photons that were shorter than 1.2 microns. These galaxies are actually invisible in the optical. It's not just that it's painful. It's like you cannot study them in the optical at all. So when we are looking at these galaxies, we're looking for galaxies that show up only in the infrared. And on the one hand, that's a pain. You got to build an infrared telescope. But on the other hand, it actually makes it very distinctive to look for them because these are the galaxies that are not visible in the optical. They're only visible in the infrared. Okay, so I'll switch into the James Webb Space Telescope, but maybe I'll pause to take some questions about galaxies. We can obviously have questions at the end as well. But, please.
Why you get a particular wavelength spiral shape? What's the root cause?
Yeah, well, that's so why? So the question is why? So sure, you have some disk. There's some little perturbation in the disk. I'm saying it's only 10%, but that doesn't say why it's spirally. And that's a mixture of things. So of course, it's driven in part by gravity, but it's also the case that the interior part of the galaxy is spinning faster than the exterior part of the galaxy. So there's a little bit of a natural tendency to advance for the inner part to get differentially rotated to pull ahead. So that is sort of what bends things into these arms. But it really is, it is an interplay of the gravitational forces that's causing these waves to propagate around.
What's the source of the angular momentum that generates this rotation?
Okay, so what's the source of the angular momentum that generates the rotation? So that is that's not really related to the spirals. That's actually when you have this big gas cloud, if it's rotating even a little bit, then as it cools and the pressure is relieved, then it will settle into the minimum energy state it can settle into is a rotationally supported disk. So this is so basically, if you have a big gas cloud and you start to cool, what stops it from collapsing into a black hole at all? Like why does it just not collapse in forever? And the answer is not actually that it can't cool enough. The answer is that it actually has angular momentum that prevents it from getting close to the center.
Spiral galaxies is the number that are rotating counterclockwise to the Earth.
Yes. Yeah. You don't have much preference as to what direction they're rotating. It could be either way just as well. In fact, we even see galaxies where there's examples of some stars that are rotating this direction and other stars that are rotating the other direction. So the gas has actually changed its direction of rotation at some point during the history of the galaxy. You can get some really weird cases that show up. Okay, any other questions? Okay, so let's go on. This will be a bit of show and tell about the James Webb Space Telescope. So the James Webb Space Telescope is, the latest and greatest NASA flagship mission. So this is really the largest thing that's happened in astronomy since the launch of the Hubble Space Telescope in 1990. If you sort of inflation adjust the costs of these things, basically, James Webb is at the scale of Hubble and is larger than anything that's come since then. It's been a long time coming. It was the top priority of the decadal survey in astronomy back in the year 2000. So basically 20 years ago. I actually joined the project in 2001. So even for me, it's been a long time coming. And when it was originally sold or argued for, people said, well, we're going to build this thing. It's going to cost $1 billion. We'll be ready in 2007, and that didn't happen. So there was lots of schedule slip, lots of cost growth, including a near-death experience, near cancellation, in other words, in 2012. So it's been a long time coming, and but it's now been successfully launched and deployed. And I think one thing I want to get across is that despite those delays, sometimes when you get delayed, like you are in trouble because like the rest of the world is sprinting past you, and you can't. There's you get out competed by the delay. But this is actually not one of these cases. Like there's a lot of questions in astronomy where you need a large infrared telescope. And this is the thing we've been waiting for. Like you can't answer these questions unless you have this. So it's going to be amazing. Okay, so why infrared astronomy? I've explained a big piece of this. So James Webb, so the Hubble Space Telescope, I should say, was an optical telescope. And in fact, it was a really good optical telescope. So it also functioned really well in the ultraviolet. In the infrared, not a very good telescope. And that's because it was polished at room temperature and optically tested at room temperature. I'm sure you can relate to this. And therefore, it must run at room temperature. And they actually take power from the solar panels to heat the telescope. So it is hot, and therefore it glows in the infrared. And it is no better than working from the ground at wavelengths longer than 2 microns. It does wonderful stuff at 1 to 2 microns. Like, no, it's been great for 1 to 2 microns. But once you get longer than that, the fact that it's a warm telescope means that we don't even build instruments for Hubble longer than 2 microns, because they're just not doing anything better than you're going to get on the ground. So JWST is optimized for 1 to 5 microns with a full range of 0.65 to 28 microns. And why is this? Well, the first reason is this cosmological redshift that I've motivated up till now, where these key features, all the optical diagnostics, all the ultraviolet diagnostics just shift relentlessly out into the infrared. And if you want to study these galaxies, you got to be in the infrared. But there's other reasons. So I mentioned the dust previously. Dust is very common in the interstellar medium. And much like the reason that the sky is blue, the sky, small particles are very good at scattering blue light and not very good at scattering red light. And so when you have this dust spread across the interstellar medium, it is absorbing and scattering bluer light, preferentially to redder light. Now, in some cases, that doesn't matter very much. I showed you nice pictures of spiral galaxies. You can see the blue light. Okay, that's great. But there are substantial, important regions of galaxies and star-forming regions that have so much dust that you cannot see them in the optical. They've been completely obscured in the optical. In the infrared, the light's sailing through just fine. So the infrared is a key mechanism for seeing through these dusty regions to study the object's interior, and in particular for star forming. Like about half the stars in the universe are born in settings that are or live in settings that are this really high extinction, these very dust obscured regions. The infrared is really important if you want to study cold objects, because as we've talked about, the cooler the object, the farther into the infrared the emission peaks. And in particular, if you want to study planets and cold stars, brown dwarfs, things like that, they peak in the infrared. So you don't get to study planets in the optical, except by reflected light from their stars, which is a fun thing to do. But mostly, if you're looking for direct emission, like you need to be studying them in the infrared. And then there's important diagnostics. So certain molecules rotate, and they have a mission that's related to the rotation and the vibration, and these tend to produce signatures that show up in the infrared. So I'm going to focus on the near and mid-infrared for this talk because that's where JWST works. There's a whole other field of far infrared astronomy that study the cold interstellar medium. Wonderful stuff, but that's not what I'm going to talk about here. Okay, so why is infrared astronomy with JWST just the bee's knees? So infrared astronomy is really hard from the ground because the atmosphere is glowing. And if you don't want to blame the atmosphere, you can blame your telescope. The telescope is reflective, but not perfectly reflective. And so it is also emitting at these wavelengths. And so when you could work from the ground, there's like 1,000 times more foreground emission if you're on the ground compared to space, if you're at 1 to 2.5 microns. And once you get beyond 2.5 microns, the thermal background from the ground just comes up and kills you. You're really losing by factors of 1 million. So as infrared astronomy, we do it from the ground because we're stubborn and masochistic, but it is working way harder than in space. If you're in space with a cold telescope, then what is actually causing you trouble? It's not the telescope anymore. The dominant emission is actually coming from the zodiacal light in the solar system. This is basically dust that's ground up from little meteorites or asteroids hitting each other, filling the solar system with little grains of stuff that are back scattering the sunlight. Okay, but scattering is peaks in the blue, so the back scattered light is preferentially blue. And eventually those things absorb some of the light and they re-emit it, but they re-emit it at the temperature of the solar system, which is like 200 Kelvin. So that's then peaking off of the red. So you have there's this window where you have the blue there's the backscattered light, which is peaking in the blue. There's the thermal re-emission, which is peaking out at like 10 to 20 microns. And there's this window at like 2 to 5 microns that's really dark. And so 2 to 5 microns is a marvelous place to work if you can actually build a cold telescope to take advantage of it. And that is great because that's where all this emission from high redshift galaxies has gone. So like it's this nice agreement of like, this is the thing, like this is where nature put the emission, and it's also where nature gave us a window to study it. And we have not done this very much up until now, some, but we haven't done a lot because you need to have good detectors to work in the infrared. And so infrared detectors have now evolved largely through military applications, but they've now evolved to the point where they work very nicely and we can exploit this window. So I'm not going to go through this slide in detail, but there's a lot of missions that are coming up to do work of various forms in the infrared, all driven by this science opportunity. Like we have the detectors, we have the window, we have the science case. Let's go build a telescope to do this, except that it's all in space. So you take 20 years to build your telescope. But we've really been trying to harness this. And up till now, these have been with telescopes that are of order of the size of 40 centimeters, 85 centimeters, 60 centimeters. So these are telescopes like this big. JWST is 6.5 meters. And for a lot of applications, you gain as diameter to the 4th power. So James Webb is like 1,000 or 10,000 times better than what we've had before. So it's not a small gain. It's not incremental. It's like factors of 1,000 to 10,000. So you can really gather the light and do in both imaging and spectroscopy. So this is the first of these missions coming up, but there's others you may hear about it from time to time that are smaller, but aimed at wider field applications. Okay, so just to say a bit about the engineering. So JWST was immensely complicated, and it's basically complicated because it's big and it's cold. And so you got to cool it, and that means you would like to cool it passively, which means you somehow have to get it in the shade. And so there's this gigantic sunshade, the size of a tennis court, basically the size of this room, that has to, where the telescope is going to sit in the shadow behind this sunshade. The whole telescope is launched out to the second Lagrange point where the Earth, the Moon, and the Sun are all behind it. So it just sits behind the sunshade and cools down to the temperature of outer space. And that's great because it's passively cooled, you're not limited by an active coolant. A lot of past infrared missions have basically launched with a dewar of liquid helium that slowly burns off to keep the telescope cold. So we don't have that problem. But of course, now it's really big. So you cannot fit a tennis court inside a rocket fairing. So that means the whole thing has to fold up. There's actually a segmented primary, this unfolding sun shield, lots of deployments. So if you look at some of the videos that came out in December and January from NASA talking about, I can't remember what they called it, 28 days. Was it 28 days of terror or 28 days on the edge? I can't remember. They had various whimsical names for it. But basically, it's because they had hundreds of these deployments that all had to work for the mission to work. Of course, anything in space, you want to make it really, really light because basically, the first driver on your cost is the mass of the thing. So JWST, although it's much bigger than Hubble, is actually only 60% of the weight of Hubble. It's actually lighter than the Hubble Space Telescope. And so to give an example of the weight reductions, the primary mirror is actually made of beryllium. And of course, it has to operate at 40 Kelvin, so they had to basically polish it warm, cool it down, test it optically, predict where the wavefront, measure where the wavefront was wrong, predict what that meant that they had to polish the wavefront at room temperature, polish that thing, and try again. They got very good at this, so they didn't have to cycle very many times. But it's just very impressive to get that stuff to work. Of course, anytime you have cryogenic optics of any form, you've got to be able to survive going from warm to cold without having the differential thermal expansion, crush things of various forms. We certainly had examples in the instrument I was involved with where people found there were certain plastic deformations that would happen at various points in the lenses. That was not good. And what's really bad about launching a cryogenic thing is that you have to have this thing that you've carefully built to hold the optics very gently so that when they you know, when the mount doesn't crush the optics as it cools, but then you're going to launch it and subject it to 10 or 50 Gs. And so it's got to not shake itself apart in the process. So it's this combination of like, it's got to be strong enough to survive launch, but weak enough not to crush itself and knock itself out of alignment when it's done. So that's really hard. And oh, by the way, it's a 6.5 meter diffraction limited telescope. So, you know, the optical tolerances are ridiculous. And you know more about that than I do, but it's been wonderful. So I think the final aspect of all this is, you know, it's one thing when something costs $100 or $1,000, you're willing to try it more than once. If it breaks, you throw it in the trash. When something costs $10 billion, failure is not an option. And so, you know, the amount of just risk reduction and review and cross-checking and everything has to go, you know, it's just amazing. So just a massive effort to try to reduce risk as it went. So yeah, as I say, like, you know, you have to unfold the telescope, it all comes out. You know, they have to unfold the sun shield, they have to unfold the primaries, and then they have 18 segmented primaries. They all have to get, you know, they all get launched, you know, out of alignment, of course, and then they have to sort of nudge them up into location. But this all went off well with the launch on Christmas Day. This is the last picture of James Webb floating away from the rocket fairing. And so after 20 years of, what did I say here, design, development, review, construct, test, retest, worry, pray, whatever you like, it all worked. And it's just, I mean, I cannot, it's amazing. And I want to stress, I take no credit for it working, but it's astonishing. So I'll show you some bigger blow up pictures here of various pieces of this, but you know, all the major optical systems of the telescope worked, all of the unfoldings, all the mechanical stuff worked, the instruments all worked. I'm actually not aware now at this point of any substantial lien against any part of the facility. So it's just marvelous. And if anything, it's actually performing better than was required, let's say. And people obviously designed for success, but it's done really, really well. So, because I thought you would enjoy it, this is a picture of aligning the 18 segments. So of course you start off with the 18 segments pointing wherever the hell they're pointing, and eventually you try to guide them back, and then they're still out of focus. So you can see that some of these are really out of focus. So the first thing you have to do, of course, is get them in focus. If you look carefully at this picture of these 18 individually focused, 1.8 meter segments, you can see that the diffraction spikes differ from one to the next. That's because secondary mirror struts have their certain patterns, and certain of these mirrors are unobscured and others are obscured by things that go in different directions. You can actually kind of see that coming together. Then you stack it to make a unphased telescope, and then you basically do phasing between the segments to bring it all into alignment. So that all worked. So this is the image that they released. Sorry, it's a little hard to see, of course, but the image that they released after this. And I was, well, this picture was pretty jaw-dropping to me, because I could actually go onto this picture. Well, even this picture, like, you can actually see airy rings, or maybe, I can see airy rings, but if you come up and squint, like, you'll see like the 8th airy ring. It's not like one airy ring. It's like there's like 8 airy rings here. It works really, really well. And this picture, like, you can see galaxies in it. So like, it's not just all stars. They have a bright star there in the center. But to give you a sense of the comparison of the ground, so this is a picture that we took from the ground of this image. And honestly, this is a pretty good ground-based picture. This is actually not a bad one. But when you flip back and forth, flip back and, well, it's hard to see. There's a lot of faint things in here as well, but it really is a gigantic improvement over what you get from the ground. No surprise, but very gratifying after 20 years of construction. And I marked like faint objects there at R of 21. If there's any amateur astronomers here, they may know what 21st magnitude is. It's really faint. So this thing is that galaxy is 1 million times fainter than what you can see by eye on the darkest site you'll ever go to. So like, these are even the things that are on this picture that look bright, not the bright star, but everything else, like everything else you see on the picture is actually already really quite faint. And the faintest things in these pictures are, 100 times fainter than that. So that's great. After they got done aligning it for a single point, the main instrument they had for the wavefront sensing instrument, they had to verify that this had actually worked across the whole field of view. This is a narrow field telescope, but when you're in the diffraction limit, even narrow field telescopes still have interesting issues across the field. And so, they have been able to confirm that the relative optics were all correctly positioned. So they actually get focus across all the instruments. This is another pretty picture they put up recently of, this is the best previous telescope at 8 microns. Honestly, a really great telescope. Like Spencer was wonderful. That's James Webb on the right. And it's just the difference of going from an 85 centimeter telescope to a 6.5 meter telescope. It's enormously better. Okay, I thought people might be interested in hearing a bit about the instruments themselves, but I won't belabor it. I know the time is running on. The telescope you refer to as the primary mirror, the secondary mirror, certain fold mirrors, and then that light gets delivered to instruments. And James Webb doesn't just have one instrument, it actually has 4 instruments that do different things with the light. So we'll have a NIRCam, which is a 0.6 to 5 micron imager and coronagraph. So that's the thing that takes the images at 1 to 5 microns. Then there's a spectrograph, which I'll show you, called NIRSpec, that takes multi-object and integral field spectroscopy. Then there's a mid-infrared instrument, MIRI, which works from 5 to 28 microns, both imaging, spectroscopy, chronography. And then there's a something called NIRIS, or fine guided sensor, which does the guiding and also has a slitless spectrograph. So, these are all different instruments. In principle, you could take data with all of these at all times. Like they're all, there's nothing that swaps between them. There's no moving parts that you select one instrument or another. In practice, so far they can run 2 of them at a time. But in principle, all of them are single light. Okay, so NIRCam is the main imager. This is imaging in 29 different filters. So you have a filter wheel that can select across 29 different filters over 2 fields, each of which is 2 arc minutes. And it actually is a dichroic, so you're actually imaging in a short wavelength part and a long wavelength part of the same field simultaneously. So all in all, it's 40 megapixels, which is not a lot in the optical anymore, of course. So in the optical, some people's cameras here have almost 40 megapixels, and an astronomical camera these days is more like a gigapixel. But in the infrared, this is the most pixels ever flown. The previous winner, I think, was 1 megapixel. So this is a big jump forwards in detector technology. And yeah, so this is, in some sense, it's just a camera. It's a really fancy camera, and a lot of these past missions have been, of course you have an imager, but it's maybe 1 filter at a time, or like 1 fixed filter or 4 fixed filters. This is really a very versatile instrument with a lot of different choices. Then the near-infrared imager and slitless spectrograph is something similar to this, but it then can introduce a grism, a grating in there, which will disperse the light out. And this is useful for getting spectra of things. But if you really want to do spectroscopy right, what you really want is a slit spectrograph. You want to distinguish you want to isolate the light from an object and take that light and disperse it without dispersing the pixels near it. So in slitless spectroscopy, you don't have anything to block the light of the regions near the object, and they're contaminated. So basically all the rainbows are overlapping. So you really want a slit spectrograph, and JWST has a very fancy slit spectrograph. So up until now, every astronomical mission ever flown in space has been with a fixed slit spectrograph. So there's no configurable thing. If you just have 1 slit, you can put it on 1 object, but the next object is not going to fall anywhere useful. So you're really doing 1 object at a time. So JWST has the first multi-slit spectrograph ever in space. So on ground, we love multi-slit spectrographs. We use them all the time. So basically, you want to go, you figure out where on the sky your objects are. and you take a custom piece of metal and you cut holes in that to match up with where the object light is going to fall in the focal plane. And you run out to your instrument, you put that piece of metal in there, and an hour goes by, you get a lovely exposure, and then you run out with the next piece of metal. But if you're in space, of course, you know, astronauts are expensive. You cannot bring up another piece of metal. You have to have some way of doing this configurably. And so this is a very fancy system where there's 250,000 magnetically activated shutters, micro shutters, that can be, you know, you basically run a programmable magnet over it and open up which shutters you want on any given exposure. So this is going to be marvelous because, you know, you can observe a couple hundred objects at a time, which may not sound like a lot, but is a whole lot more than one. So really gigantic gain in multiplex. And so I think this is going to be really remarkable. We've really not had a spectrograph that's capable of doing faint object spectroscopy at 2 to 5 microns ever, or at least not since a sort of prototype instrument in 1995. This is going to be wonderful for studying galaxies at high redshift and all different sorts of things. And then finally, going off into the mid-infrared. The mid-infrared here is 5 to 20 microns. This requires a change in detector technology, but they built a very versatile instrument, and so it does imaging, spectroscopy, coronagraphy. It's really nice. This is also remarkable that it uses a cryocooler. So this part of most of the parts of James Webb are operating about 40 Kelvin, including the detectors. But these detectors have to run much colder, and so there's actually a cryocooler, again, taking power from the solar panels to cool this part of the telescope down to 4 Kelvin. Okay, so other challenges. So JWST is cold and large, but it's also floppy and shy. So the floppy refers to the fact that it's really big and it's really light. And so when you slew James Webb and it gets to its new spot and you say it's a stop, it just sits there and stops and jiggles for like 30 minutes. So it does not reconfigure and point easily. It takes basically 30 minutes to slew from one field to the next field. And so when you go to do your observations, it's really built to do long exposure. This is not a point and click telescope. And then shy because it has to sit behind its sun shield, and at any given time, it can observe. So if the sun's behind me, you know, there's a sun shield, and the telescope's looking out, let's say 90 degrees relative to the sun shield, so like transverse to the direction. So it can rotate and it can observe anything in some region transverse to that, but it can't look straight out, and it certainly doesn't look back towards the sun. So at any given time, you can observe about 35%, or I said 39% of the sky on any given time. But then the whole thing rotates. You know, as the year goes along, that region rotates around. So you have to plan for the orientation. You have to plan for when your fields are going to be observed. There are substantial constraints about how you do your observations, but that's life. Okay, so what I work on is something called JADES, which is, I'm a member of the near-infrared camera instrument team, and we've joined forces with the near-infrared spectrograph team to pool the time that was allocated to these instrument teams to do this very deep survey of the sky. So this is basically the Hubble, you know, the James Webb equivalent of the Hubble deep field, if you remember the famous Hubble deep field pictures. This is James Webb's version of it, but, you know, it's James Webb, so it's fainter, redder, wider, better. So we're very excited about this, and we'll be doing a lot of spectroscopy along the way. And again, the goal is to be isolating these galaxies out that are far away, whose light has been shifted by a factor of 10 or more, to try to discover the earliest galaxies that we've, you know, yet been able to observe. Okay, so this is my last slide. So James Webb has been a long wait, but is going to be amazing. Really a transformative mission, because the basic attributes of the mission have been, you know, the top of astronomers' wish lists for the past 20 years, and, you know, nothing's been able to come along to scratch that itch. So it's just critical for viewing the earliest galaxies, for cutting through interstellar dust to see the coolest stars and exoplanets. And it's, you know, we all hope that it would go well, but it has really gone well, and it's just actually, that's amazing to see all the engineering come together to do this. So science operations will be starting in July or August. I don't know exactly which, but it's been about 6 months of commissioning. And so hopefully the data will really start to flow out in August. They are running a really nice blog that posts every, few days. So if you're interested in sort of following about the sort of deployment and commissioning of the mission and some of the other sort of just aspects of the mission, they've actually done a really nice job of it. So I encourage you to follow it. Okay, with that, I'll take questions. Please.
Yeah, who's responsible for evaluating the observation proposals and then scheduling the observations?
Okay, so the question was, who actually sort of handles the scheduling of and the selection of proposals? So that's the Space Telescope Science Institute, which of course is doing this on contract from NASA. And indeed, as you say, there's a competitive proposal process that runs once a year where people, send in their proposals. In the first, they've done one round of the selection so far. The oversubscription was about 5 to 1, which is actually not as bad as I was fearing. So Hubble was 10 to 1. 5 to 1 is okay. Of course, so I should say that that's done by peer review. So although Space Telescope is running the panels, they are actually, they are not themselves making the decisions. Those decisions come from people they invite to serve on those panels. And it's, oh gosh, I mean, they probably have to invite 150 people to serve on the various panels, but to do proper evaluation of lots of proposals. And then once those proposals are selected, then Space Telescope is in charge of scheduling them and actually operating. Yeah.
Question. One, how international is the team, the selection of astronomers for that? And the other is with all the risk stuff, what are the odds of having gas or micrometeorite or something damage over the 20-year?
Yeah. Okay, the first question is how international is the project? So JWST is led by NASA, but has a large or at least substantial contribution from the European Space Agency and also from the Canadian Space Agency. So those are the groups that built the telescope. When they go to operate it, actually it's operated on worldwide proposals. So anybody in the world can write proposals. And so the teams that come together to write these proposals, most of the time these days, it's not a single person on an observing proposal. It's usually a group, maybe 5, maybe 50, but usually those teams are pretty multi-institutional and at this point fairly international often. And then the second question is what happens when a micrometeorite hits? And it can happen, right? So and it will happen. Hubble, of course, has been up there for 30 years, and it's still plugging away. So they do have to build these systems to be robust to that sort of stuff. Having a micrometeorite sort of come through the sun shield just makes a little microscopic hole in the sun shield. That is okay. The sun shield has 5 layers, so you're not, you don't let a lot of light through. Of course, you can always be in the world where you get even less lucky and that thing actually hits something vital. But the vital things are pretty small and they're redundant. So I'm not aware of any. I'm sure there must be an example, but we have not lost a major astronomical satellite to a sort of meteor catastrophe. We lose them to other reasons, but we have had things fail, but it's not because they get hit by micrometeorites.
2 questions. The first will probably give you your last belief, but I'm guessing that when you talk about a ship, you're always referring back to this hydrogen fundamental line, and you just have to assume that all the radiation is coming from that moiety. Is that sort of the?
Well, not all the light is coming from hydrogen, and that little double pinprick that I showed you in those plots, that's not hydrogen, for example. That's calcium lines. But so all the atomic species have characteristic patterns, and hydrogen is very prominent, but it's not the only thing that we observe. And in fact, a lot of the characteristic frequencies that get emitted by stars and galaxies is not being set by hydrogen.
I'm a little lost how you know a ship is coming from a certain.
You have to see the patterns. So if you just saw a single line, then you would not be necessarily highly confident in that in the identification that that line came from a particular element. If you see two lines, then the ratio of the wavelengths is very distinctive, and like the ratio of the wavelengths is invariant under this shift. So anytime you see multiple lines, you're in good shape.
My second is an engineering question. Is there ever consideration that, to put it sort of coarsely, you've got a $10 billion program with 4 nines of success? Is there any ever consideration of saying doing 2 $1 billion programs with 2 nines? How does that?
Yeah. So the question is, at what point do you build more than one of something and try to cut costs on both of them? I'm sure they do think about that. But it must be the case that the trades don't actually favor it, because they've never, I'm not aware of any major space program that's taken that, or at least not astronomical program that's taken the we'll launch 20 and let 10 of them fail approach.
In manned space flight, that works. And,
Yeah.
But of course, there's a political aspect that you lose somebody, some percent of the time, which is not really powerful.
Yeah, we have had examples of missions that were launched where people decided to rebuild the mission and fly it again, or at least fly something similar to it again. So that has happened. But the idea of actually wheeling 2 of them out to the launch pad and hoping that one of them gets to orbit has not done that. Although I don't think it's crazy. Like I'm not actually I'm not talking it down. I'm just saying, like, it must be that the trades don't end up favoring that. In the back.
So Doctor, so you said it took 20 years for you guys to develop this and launch it. How long will it stay in full use?
Great question. So how long will it? Yes. So it was required to last for 5 years. So the design requirement was 5 years with a goal of 10. But it turned out that the launch was really, really, really accurate. And so this thing is sitting up at this second Lagrange point, which is sort of like sitting on top of a hill. And basically you shoot it up and you have to land just short of the top of the hill so that you can keep with just a little bit of propulsion, pushing it up to the top of the hill and keeping it from falling off. And the Ariane space launch was so accurate that they actually are going to save a lot of propellant. They didn't have to burn very much extra propellant. So now they think they have 20 years of propellant. So maybe it will last for 20 years unless something else does, like the micrometeorite. But so that's a really big deal, because if you have something for 5 years, like you think about it in human terms, if you have something for 5 years, okay, a graduate student can come in, do a nice thesis on the project, but by the time they're ready to go on and make a career for themselves in faculty life, the thing is gone and you don't have another one, which means like you've gotten all trained up in a field that is just evaporated, or at least in a in a system that's just evaporated. 10 years makes that a little better. You're not totally, don't totally have egg on your face, but it's still shorter than the time between these major projects. If it actually lasts for 20 years, that actually bridges you out to the point where somebody who's working now, who's getting started, actually will have a vibrant career, including faculty life, long research career on this one telescope, and maybe it will last about as long as it takes us to get the next major space telescope built, even if that thing is not infrared optimized. So to me, that was like some of the best news. Like maybe this actually got onto a time scale that's actually career friendly, even though the science will do good for 5 years. Yeah.
So what is the next big 20-year program? Is there one?
Yeah. So I said this.
Hopefully not 20 years.
Well, it will be 20 years for some of the stuff, but I said that this came from the 2000 decadal survey. The 2020 decadal survey was released this past year, and that considered 4 different flagship mission concepts. It didn't actually come out and say build this one. It basically it directed NASA, or advised NASA, I should be really clear, it's not directed, but advised NASA to do additional development work on one of those concepts, which would be a large optical telescope, and to then do additional development on an X-ray and a far-infrared mission. So I think today it is not clear what the next of these flagship missions that's at an early stage in design will be, because there's a mission that has sort of been given the front step, but it has to then demonstrate that it can actually control cost and actually get itself built. So in terms of the next thing that's going to be that's at the design phase, that's the answer. NASA is actually building a large telescope called the Roman Space Telescope. And that is scheduled for launch in 2026, I think, maybe 7. But so that's in active construction. So I'm just saying, like, that's not in the approval stage. Like that is really being built now. That is also an infrared optimized telescope, but for wide field astronomy, and so it's a 2.4 meter telescope. So it's also going to be quite great. That's another aspect of why having JWC last longer is such a wonderful thing. It's like now we're actually going to have this wide field telescope operational, so we can find the interesting objects that we then can go and follow up with the big telescope.
What's the data product release? Like, is the data products going to be released probably?
Yeah, so data. So the question about data release. So data does get released from all these space telescopes on the timescale of about a year. Now, so if you just write a proposal and don't do anything different, then you get the data immediately, and it goes to the archive a year after you get your data. But a lot of proposals, in order to get a competitive advantage in the time allocation process, choose to waive that proprietary period. So there's actually going to be a lot of data hitting the public domain in July and August. As like as soon as they start taking data, they'll be flooding into the archives, and there'll be a bit of a feeding frenzy, but yeah, that's okay.
What do you expect to discover on a global scale?
So it'll be a lot of different things. So for the type of work that I'm talking about, basically we'll be able to discover galaxies earlier in the universe than we've seen them before. But I think more importantly, we'll be able to really study them in great detail, where we're finally seeing, large chunks of the spectrum and being able to take spectra of them to have the diagnostics of the interstellar lines and the diagnostics of the stellar population. So to me, it's like understanding that early generation of galaxies, and trying to see how they behave in comparison to galaxies that are more mature. But more generally, the telescope does, there's not really almost no area of astronomy that is untouched by what the telescope will do. So, whether it's studying exoplanet atmospheres or star formation or, nearby galaxies, just everything, the program is very diverse. In the first year of the mission, they approved about 100 different observing programs. So it'll be doing a bit of everything. Please.
I have no knowledge of what the second point is, like, lines or earthly distances.
Oh, five.
Geosynchronous or
Yes,
orbit
right.
or
Yeah, so the question is about the second Lagrange point. So it's 1.25 million miles, so it's about 5 times the distance to the moon. But physically what it is a point out. So if you go from the sun to the Earth and then another 1.25 million miles, and it's the point where so as you move further away from the sun, things are going to rotate slower. And this is the magic point where the extra gravity from the Earth causes that circular orbit around the sun, to be exactly 1 year. So it's going to rotate that point rotates around the sun at the same rate that the Earth rotates around the sun. And it only gets to do that because it has the extra gravity from the Earth. So it's this sort of metastable point there that's like it's a very nice place to do astronomy, because you get far away from the Earth, but not too far, and keep the Earth and the moon and the sun all behind you, and so you can get cold. So there's other astronomy missions out there as well.
Okay. So not much space to pretty over.
Well, there's still a big region, so they're not crashing into each other.
But my second question is, these things are planned like years and years and years, and designed years, and usually by the time you send it up, the computer is totally obsolete. Nobody will talk it, and do you feel like this is still up to the minute? Or do you say, oh my God, we only had that, 5 years ago? Or, I mean, you clearly you're super excited because it's unique, but.
Yeah, so the question is basically, when projects take a long time, do you get worried that they become obsolete before they launch? And I think, on the computing side of things, sure, it's, the computers that are on this thing are old. But I don't feel like the computing is really the limiting factor in the mission. So to me, the key technological advance we most want is in the detectors. If you had more, better, cheaper detectors, you would obviously like to build, do more of that. And So in that sense, if you're building one today, then you would build it with more pixels. And indeed, the Roman Space Telescope is not 40 megapixels, but something more like 400 megapixels. Because of that, trying to capture that opportunity on the detector technology. So I would say that is the biggest piece of that. I'm sure that there's aspects of the engineering where people would sort of, there have been some advances, but I think that's mostly around the edges for that side of things. And I would expect, but I don't know, but I would expect that the rocket technology, the reason we had such a good launch was because they actually had improved their rocket technology over the years. So I don't think that was a total accident. I think they knew what they were doing.
Questions from the chat.
Please.
So the first one is, does the interstellar medium re-radiate at ambient temperature? How does that affect?
Yeah, so does the interstellar medium re-radiate at its ambient temperature? And the answer is yes. So when you have these dust grains, they're out there at temperatures that range from like 10 degrees above absolute zero to maybe 50. It's a complicated emission, and so the emission is more complicated than just saying, oh, it's like a black body at this temperature. So there's more going on than that, but basically, yes, it's characteristic. The characteristic temperatures are very cold, and the emission is correspondingly related to that.
The next question from the chat, and I invite the pastor to unmute himself and ask it. Did the slide show the instrument map to image show unmapped image?
So the question is, I think the question is this map? I believe the question is this map at equal? Is this actually the field of view on the sky? And the answer is yes. And maybe if that's not the question, then I'll unmute and clarify.
Third question from the chat is, can you explain the difference driving resolution? What is driving the resolution difference between the Spitzer telescope and James Webb, the JWST? JWST is at 20, Spitzer is at 4, so better SNR, better sensor resolution.
Okay, so I think they mean angular resolution here, and that's really being driven by the diffraction limit of the telescope. So that's not, all these telescopes are basically in the diffraction limit in space, and so the F ratio of the telescope doesn't change that fact. So it's really, the difference between being at the diffraction limit of a 0.85 centimeter telescope, an 85 centimeter telescope versus a 6.5 meter telescope. And so remember, the diffraction limit is basically set by the ratio of the wavelength of light to the diameter of the pupil. Please. Okay, yes. Okay, so the first question was, what's the limiting exposure time with the detector arrays? This was actually debated because we weren't sure what the cosmic ray flux would be. So you ultimately get limited by the cosmic ray hits on the detector pixels. It appears that about 1,500 seconds, about as long as you want to go. So we basically build up that you could take many exposures, and you in fact want to take many exposures and moving around, dithering around a little bit. But basically, 1,000 to 1,500 seconds that's about the right amount of time. And the second question, sorry, the limiting magnitude, right? So the limiting magnitudes get down to about 30th magnitude. Now remember, magnitudes are a logarithmic system, so every 5 magnitudes is a factor of 100 in flux. So this is 10 billion times fainter than the faintest naked eye things that you'll see. I should actually go ahead and I should figure out how many photons one has actually collected in that exposure, but I think the photon incoming rate must be something at the level of 10 per exposure. So one photon every 10 to 100 seconds or something. Thank you. It's been fun.
See you all. Yes.
Stop video.
Very nice.
Oh,